Today we're going to look at Chapter 4 review. There are quite a few concepts that I want to touch base on again. So looking at a base of E, compound interest, solving some application problems, looking at exponential growth and decay models. So when we're talking about compound interest, it is after T years, the balance A in an account with principal P and the annual interest rate R, which has to be written as a decimal, is given the following formulas. If we're talking about N compoundings per year, then we use the formula A equals P times 1 plus R over N, all raised to the NT power. If we're talking about continuous compounding, we're using A equals P times E to the RT power. So anytime you hear the word or see the word continuous, we know we want to have a base of E. However, if we have other vocabulary words and then we're talking about compounding, we're going to be using that first formula where we have to know what N is. So a quick reminder, compound interest, if we're talking about compounding annually, then N equals 1. Semi-annually, N equals 2. Quarterly, N equals 4. And monthly, N equals 12. So let's look at a few examples. It says a sum of $10,000 is invested into an annual rate of 8%. We want to find the balance of the account after 5 years when it's subject to first quarterly compounding, then when we compound monthly, and then finally when we do continuous compounding. So the fact that part A says quarterly, that tells us that we're going to be dealing with an N value. Quarters, we're talking about 4. $10,000 is invested. That's your initial amount. So that's going to represent that principal P. The percent here is our rate, but remember, I want rate to be written as a decimal. So I can take that percent, I can divide it by 100, or you can go from the decimal, which is after the 8, and move it 2 places to the left. So really we want 0.08. And then we're talking 5 years, so that's a length or amount of T. So we have everything that we need to plug it into our formula. So remember, A equals, we want our P value first, so 10,000. And then in parentheses, 1 plus our rate, which was 0.08, being divided by our N value, which is 4. Close parentheses, and then our exponent is N times T, so 4 times 5. Now, using your calculator, you want to very carefully type all of that in. Careful not to lose parentheses. Careful not to lose, like 4 times 5 is an exponent. So make sure that you're just like very, very careful when you're typing all of that in. And so we are talking money and we're investing. And so after 5 years, because it's 8% really growth, we should be getting a number that's bigger than 10,000. So we should end up with $14,859. And we're talking money. So 2 decimal places, that'd be 47 cents. And there is our amount compounded quarterly. If I'm talking monthly, well then our N value is 12, but everything else in our problem is the same. So A equals 10,000 times 1 plus our rate of 0.08, but now we're dividing by 12, and now that's raised to the 12 times 5 power. So once again, just very carefully typing all of this into your calculator, making sure that you are careful not to lose parentheses and all that kind of stuff. Our exponents, 12 times 5, make sure you're careful there. And when we type that in, we should get an amount of $14,898.46. So notice that quarters, you're talking 4 times a year. Monthly, you're talking 12 times a year. So it should make sense that compounded monthly is bigger than compounded quarterly. Lastly, here we want to continuously compound. So remember, continuous means that we have a base of E. So we have A equals our initial amount, so 10,000 times E to the rate, which was 0.08, times our time, which was 5. So remember, you have that E button in your calculator. So very carefully make sure that you are doing that. Make sure that you then have the rate and the time as an exponent, and we should have gotten then $14,918.25. So when your initial amount, your rates, the amount of time, when all of that's the same, depending on what you are compounding, is going to tell you how which one should be the biggest. Continuous is going to be more times a year than monthly and quarterly. So once again, that's why that value should be the biggest out of all three when all the other information is the same. Here I'm giving us a formula. R equals 6 times e to the 12.77x power. X is representing blood alcohol concentration. R, given as a percent, is the risk of having a car accident. So the question asks what blood alcohol concentration corresponds to a 50% risk of a car accident. So notice the number they're giving us is 50%. R is given as a percent. So I'm going to substitute 50 in for R into this equation. And notice that what I'm trying to find is the x value from my exponent. So in order to start solving for x, which is in our exponent, I need to get x out of the spot of an exponent. So to do that, I first want to isolate that base of e by itself. So I'm going to divide both sides by 6. Okay. And so when you don't have the nicest number, like 50 divided by 6 is a repeating decimal, I'm honestly just going to leave it as a fraction so I don't do any rounding, so I don't have a chance of getting farther away from the most accurate answer. So I am just going to leave it as 50 over 6, and now that equals e to the 12.77x power. So now my goal is to get rid of that base. So remember, if our base is e, I need to know what's the inverse of e. And so what we've been talking about with logs is that the natural log is that inverse. So I'm going to take the natural log of both sides. And so by taking the natural log of both sides, which I had to do to both sides because if you're dealing with an equation, you want to keep them balanced, the whole point is that the natural log and that base of e are going to cancel. So that gives us then the natural log of this 50 divided by 6, and now that just equals 12.77x. So last step to get x is to divide by that 12.77. And so then I want to know what X is because X is representing the blood alcohol concentration. So you just need to very, very carefully type this into your calculator. Notice that 50 divided by 6, after you do that natural log button in your calculator, make sure you close the parenthesis before you then divide by that 12.77. Otherwise, you're not going to get the correct answer. So if I then look at this, we have roughly then 0.17. And so that would be the blood alcohol concentration. Here's another formula. It's modeling the population of Florida in millions T years after 2000. It's asking when will the population of Florida reach 19.2 million? So I don't know what that year is to reach that amount. That's what I'm going to try to find. So that 19.2 is going to go into the A in our equation. So we'll have 19.2 equals 15.9 times e to this 0.0235 t power. So just like our last problem, our goal is to get t by itself, but right now it's an exponent, so I have to isolate that base of e by itself. I'm going to divide both sides by this 15.9. And once again, I'm not going to fully divide that out yet. I'm going to leave it as a fraction. So we'll still have this 19.2 over 15.9 because I don't want to round until the very, very end. And like our last problem, now that I just have that base of e isolated by itself, I need to get rid of that base so I can just have the term that is now the exponent. So to undo that base of e, I'm going to take the natural log of both sides. Because the natural log and e are inverses of each other. So now we have the natural log of this 19.2 divided by 15.9, and that equals this 0.0235t. So to get t by itself, we're going to divide by that decimal. And then once again, when we're typing things into our calculator, we're going to be very careful. After you do your 19.2 divided by 15.9 from taking the natural log, you have to close the parenthesis before you divide by that decimal of 0.0235. Make sure that you don't lose any of those zeros when you're doing your decimal. And so we get t to be approximately 8. It's 8.025 and so on and so forth. So when is the population going to reach that? Well, it's going to be approximately 8 years after the year that the model's telling us. So add those two together, and that tells us that in 2008, we get that population in Florida to be 19.2 million. Okay, last concept I want to really quick review, exponential growth and decay. So remember, if I'm giving you this model of A equals A sub O times E to the KT power, K is going to tell us what kind of model we have. It's a growth model if we're dealing with a positive number, something that's greater than 0. It's going to be a decay model or decreasing if that K value is negative or less than 0. So it says in 1990, the population of Africa was 643 million, and by 2000, it had grown to 813 million. So we're going to use that growth and decay model. T is the number of years after 1990, and we're going to find the growth function that models the data. So basically, when it says the growth function, we're going to be figuring out what is that K value. All right, so using our information, it says in 1990, we're dealing with 643 million. That is your initial amount. That's your A sub O value. By 2000, it's now 813 million. So that's what it's ended up being. That's our A value. So now what is our T? Well, our T value is going to be years after 1990. If we're now talking about 2000, because that's where this 813 million comes from, we have to then figure out that difference. So the difference would be 10 years. So now I have everything except for K, because that's what we're going to try to find, so I can substitute all these values in. So when we do that, now our equation looks like this. And just like our last several problems, we can go ahead and now start solving for K. So I want to isolate to get that base of E by itself. So I'm going to divide both sides by 643. Once again, not fully dividing this though, because I don't want to do any rounding until the very end. I'm going to switch the K and the 10 around. It means the same thing. Just like all our other problems, now I just got to get rid of that base of E. So I'm going to take the natural log of both sides. That then cancels that out. And so to get K by itself, I know that since 10 is attached to it through multiplication, I'm going to divide both sides by 10. And then carefully typing this into our calculator, we are going to get a pretty long decimal. So I would like you to round it to 3 decimal places. So we've got 0.023 as that value. So then let's use that new K value that we just created. So from that last example, our K value now is the 0.023. Once again, 1990, we have that initial amount or that A sub O value to be 643 million. And once again, we know that it had raised to 813 million by 2000. However, I don't really care about that value anymore because now the question says, by which year will Africa's population reach 2,000 million, which is basically 2 billion. So now I want my A value to be represented as this 2,000 million. So we're going to have our 2,000 here. We'll still have our initial amount. Now I have my K value, but I don't know what T is. I'm trying to figure that out. So just like all of our other examples, I'm going to start isolating that base by itself first. I'm not going to divide this quite yet. I know that to start then solving for the variable that's in my exponent, I have to get rid of the base. So because our base is e, we're taking the natural log of both sides. And so that is going to cancel that out. And then finally, we'll divide both sides by this 0.023 and very carefully type all of that into our calculator. When we do that, we get our value of t to be approximately 49.34. So once again, the question says by which year. Don't forget that we're talking about our model, which starts in the year 1990. So since 49.34 is closer to 49 than it is to 50, I'm going to add 49 onto 1990. And so that tells us that it's the year 2039 that gets us that population in Africa to be that 2 billion mark.